Hello everyone, so in this tutorial we're going to learn how we can build a state diagram from a given circuit diagram. So this is the question. We need to build a state diagram from this circuit diagram. So at the very beginning we need to find out some specific information from this diagram. We need to find out the present state, next state, input and output. Okay, so we can see that there are two present states, A and B. So how do we get sure that we have two present state in this diagram? So we have to look at the diagram and we have to find out how many flip-flops are there. So we have two different flip-flops, we have two separate flip-flops, so both of them are D flip-flops basically, but we have two flip-flops. So the number of present state will be same as the number of flip-flops. So there are two flip-flops, so there will be two present states. And how can we denote the present states? We can just use the variables that are given as the output of the flip-flops. So this would be given in the question. Alright, so here the outputs are given as A and B for two flip-flops, and we can just use A and B for our states. So we have two flip-flops, so we'll have two present states, and we'll denote them using A and B. So the present states would be A and B. Okay, so if the present states are A and B, so the next state would be A plus and B plus. Okay, and the inputs, okay, when we say input, we mean that we have to consider the circuit external inputs, which is X, only X in this case, and also the flip-flop inputs. So here we are using D flip-flops. Alright, there are two D flip-flops. So in case of D flip-flops, there is only one input, right? So there are two flip-flops, so basically in total there would be two different inputs. Since both of them are D flip-flops, so if we just write inputs as D, comma D and X, so in this case if we write both the inputs as D, then they would be undistinguishable, right? So we have to be able to distinguish or separate them. Okay, so for that purpose we're just going to denote them as DA and DB. For the first flip-flop the output is A, and for the second flip-flop the output is B. So we're gonna consider the first input as DA and the second input as DB. Okay, so the inputs would be DA, DB and X, and in case of output we'll only consider the circuit's external outputs, which is Y in this case. So it's not always fixed that there will only be one output in the circuit. So that means some circuits may have more than one output, or some circuits may not have any kind of output at all. Alright, so this could be different in case of other questions. Okay, so just to recap, we have to find out this four specific stuff from the given circuit diagram. We have to find the present state, and the present state will be same as the number of flip-flops. So two flip-flops, two present state. So the present states are denoted using the variables given in the question, okay, A and B, and the next state would be A plus and B plus, and the inputs would be the flip-flop inputs and the external input, and the output is only the external output. Okay, so this is the very first part. So in the next part what we'll do, we'll try to find out the equations of DA and DB. Alright, so let's consider the equations. So here DA comes from this OR gate, and this OR gate comes from these AND gates, right? So in the first AND gate we can see that one part is coming from A, right? So this is A, and the other part is coming from X. So basically this produces A dot X, right, or AX. And in the next AND gate one part is coming from X and the other part is coming from B. So this is basically BX, and AX and BX goes into this go into this OR gate. So this right here, DA, actually produces AX plus BX, right? So DA equals to AX plus BX. So this is the equation for DA. Similarly, we'll find out the equation for DB, and we'll find out the equation of Y. So what are we doing? We're trying to find out the equations for flip-flop inputs, okay, the flip-flop inputs and the external output. So in the next step we're going to find out the flip-flop input equations and the external output equations. So I've already derived the equation for dA. Similarly, you can derive the equation for dB and y, and if you derive the equations, then you'll get something like this: dA equals to x plus bx, dB equals to a prime x, and y equals to a plus b into x prime. Alright, so these would be the equations for the flip-flop inputs and the external output. Okay, so this is the next step, and after this step then we'll try to build a table, and that table is known as the state table. Alright, so we'll build a state table. So in case of state table, so there will be two part. In the left part we'll write down the present state and the external input. The present states were a and b, and then external input was x. So three separate variables. For three variables there would be 8 different combinations from 0 to 7. All the binary numbers are written here. Okay, and in the right side we'll write down the variables of the equations that we just derived a few minutes ago. Okay, so we derived equations for d and db and y, that means flip-flop inputs and the external output, and we'll write down those variables here. So dA, dB and y. Okay, now we know the equations, we got the input values. Alright, so we can just write the values for all of these columns. For example, dA. Okay, so dA equals to ax plus bx. So for the first row we can see that a, b, x all are 0, right? So if we put 0 here, okay, so ax plus bx produces basically 0, right? So that's why dA is written as 0 here. Similarly, we can do it for the next row and the next row and for all the rows. Alright, so this is how we can calculate dA. Similarly, we can calculate the value for dB. We can just use the equation for dB, and we can just use the values given here. So this is almost the same as the writing down truth table. Alright, so we can just use the values from here, and we can use the equations from here, and we can write down the values for dB. Similarly, we can do it for y. So once we get all of these values, we'll just expand the state table. So now it's time to expand the state table. Okay, once we get all the values, we can just expand the state table, and after expanding we'll add 2 more columns here. So these would be the next states. Alright, the present states were a and b, and the next states would be a plus and b plus. Okay, now we have to learn how we can write down the next state, a plus and b plus. Okay, so this part over here we have already calculated this in our previous slide, right? So now we're going to calculate the next state. So when we want to calculate the next state, we have to remember something. So here you can see that there are 2 columns, a plus and b plus. So when we want to calculate a plus, we don't need to consider both dA and dB. We only need to consider dA, and we don't need to consider a and b. We only need to consider a. Alright, so when we want to calculate a plus, we only need to consider everything regarding a. Okay, and when we need to consider, when we need to calculate b plus, we only need to consider everything regarding b. That means dB and b. We don't need to consider anything regarding a while calculating b plus. Okay, so you have to understand and remember that. Okay, so let's calculate a plus. So in case of a plus, okay, so for the first row here, so since I'm calculating a plus, I'll only consider dA and a. So I'll go to dA and I'll see what the value here is. So in case of the flip-flop input, I get 0. Okay, so now I need the help of the truth table for D flip-flop. Since this question is related to D flip-flop, so I'll need the help of the truth table of D flip-flop. So this is the truth table of D flip-flop. If the flip-flop input is 0, then the output would be 0, and if the flip-flop input is 1, then the output would be 1, right? So here the flip-flop input is 0, so the output is 0, so that means the next state would be 0. Okay, in the next row the flip-flop input is 0 again, so the next state would be 0 again based upon the truth table. Flip-flop input 0 and next state is 0, and when the flip-flop input is 1, based upon the truth table the output was 1, so that means the next state would be 1. Similarly, we can calculate all the values for a plus, and we can do the same thing for b plus, but while calculating b plus we don't need to consider dA and a, we'll only need to consider dB and b. Okay, and you have to check something here. When I'm calculating a plus or b plus, I can see that I don't actually need to check anything from a and b. Alright, so remember, when you calculated a plus, we just saw dA, then went back to the truth table, then just saw the value and just wrote down that value directly. So we didn't need to check the present state, right? So that's because in case of D flip-flop, the truth table doesn't have any kind of not used or no change or toggle or something like that. Okay, the D flip-flop truth table did not have those specific conditions, the specific combinations. So that's why for specifically D flip-flop, to write down the next state, we don't actually need to consider the present state. So that means the present state doesn't have any kind of effect on the next state. Okay, and this is only true for D flip-flop. In case of other flip-flops, it may change. All right, so again, if you want to calculate b plus, you need to consider dB and b. So here the flip-flop input dB, so we can get 0, and we go back to the truth table, we see that if the flip-flop input is 0, then output is 0. So that means we are getting a value directly, so we'll just write down that value in our next state. In case of 1, we're going back to the truth table, we see that if flip-flop input is 1, then the output is 1. So that means our next state would be 1. So here the next state is 1. So this is how we can build both a plus and b plus. So once we're done with this, we can go to the state diagram right now. So just to make it more neat and clean, we're going to ignore the flip-flop input parts right there, and we're going to cancel them out from our table, and we're going to write the table again like this. So we just cancel the flip-flop inputs, and this is the a more neat version of the previous table. Okay, now we are going to draw the state diagram. Okay, so to draw the state diagram, we have to create different states, right? So we're using here 2 flip-flops. The circuit had 2 flip-flops, remember. So the formula is if you have m number of flip-flops, then you'd get 2 to the power m number of states. So we had 2 flip-flops, so you'll be getting 2 to the power 2, so that means 4 states. So the 4 states would be 0 0, 0 1, and 1 0, and 1 1. Okay, so here we can see that if the present state is 0 0 0, okay, so a and b are present state, remember. So if the present state is 0 0, then for input x the next state would be 0 0. Okay, if the present state is 0 0, then for input x the next state, a plus and b plus are next state, right? The next state would be 0 0. So that means for 0 0, if the input is 0, then the next state is 0 0 again, so I go back to the 0 0 state. Okay, and for this specific input the output was 0. Why was the output? So the output was 0. So I'll also write the output in the diagram. So the rule for writing the output is just giving a slash notation and then write the output on the right side of this slash. Okay, so I'll write 0 here. So let's check another. So if the input is if the present state is 0 0 and the input is 1, then the next state would be 0 1. Okay, so from 0 0, if the input is 1, then the next state is 0 1, right? And the output is 0. So here's the output. Okay, now for 0 1, if the present state is 0 1, then for input 0 the next state is 0 0. Okay, so for 0 1, if the input is 0, the next state is 0 0 and output is 1. So here the output is 1. And for 0 1, if the input is 1, then the next state is 1 1. 0 1, input is 1, so next state is 1 1 and output is 0. Okay, I think you get it by now. And for 1 0, for if the present state is 1 0 and input is 0, then the next state is 0 0. Okay, so here from 1 0, if the input is 0, then the next state is 0 0, right? And output is 1. Okay, and for 1 0, if the input is 1, then the next state is 1 0. Okay, so that means I go back to 1 0 again if the input is 1 and output is 0. Okay, and for 1 1, if the input is 0, then the next state is 0 0. So I go here if the input is 0 and output is 1, and for 1 1, if the input is 1, then I go to 1 0, right? And output is 0. Okay, so this is the final state diagram for this question. So if that doesn't seem neat and clean to you, we have another diagram here. So it's basically the same diagram, so it's a much more cleaner version here. Okay, so now it's being overridden with whatever I have written here. Okay, but this is basically the cleaner version for this diagram. All right, so this is how we can build a state diagram. Okay, and you don't need to put 0 0 0 1 1 0 1 1 like me. You can put them in any way you like. Okay, you can even put them one after another. Okay, so 0 0 0 1 1 0 1 1, so you can put them like that too. So you just need to think about the transitions. Okay, so doesn't matter however you put your combinations, it doesn't matter however you put your states, your transitions, the arrow signs will always be the same, because everyone is doing this, is building this state diagram based upon this specific state table, right? So everyone is building the state diagram based upon this state table. So it doesn't matter however they put their states, it doesn't matter what type of organization they use. Okay, their transitions will always be the same. Okay, so this is how you can build a state diagram from a circuit diagram. Okay, so this is just one problem, and we'll see another problem similar to this one. So let's go to that problem. Okay, and this is the cleaner version of that diagram, just what I drew a few minutes ago. Okay, so this is the cleaner version of that diagram. So this is the end of example 1. Now let's check out another example. So this is example 2. So this is another example of building a state diagram from a circuit diagram. So this is the circuit, and you can see that in this circuit we did not use D flip-flop, we are using JK flip-flop here. And just like the previous one, we need to find out the present state, next state, input and output. And since we are using two flip-flops, there will be two separate states, and the variables are already given here, the output variables, which are A and B. So the states would be A and B, and the next states would be A plus and B plus. And inputs, in case of this question, we are using JK flip-flops, right? So in case of JK flip-flops, we have two inputs in one flip-flop. So if we have two flip-flops, that means we have 4 inputs in total. So just to distinguish among them, we can count it as JA and KA, and for the bottom one we can count them as JB and KB. All right, so 4 inputs for the flip-flops and 1 external input X. And for this circuit there is no output, right? So it's not always fixed that you'll always have a output. Okay, you might not have any kind of output at all, just like this one, or you might have more than one output. Okay, so these are the initial stuff, and now we are going to find the equations for the flip-flop inputs. So that means we are going to find the equations of JAKA and JBKB. all right, so if you take a look, the JA, so the JA, this part came directly from this part, right? So that means JA equals to B, right? And this is what is written here, JA equals to B. Similarly, you can calculate the equations for KA, JB and KB. And okay, so similarly you can calculate the equations for KA, JB and KB, and you would get eventually these equations. So once you get these equations, then you will build the state table like the previous problem. So in the state table you have two parts. In the left part you have the present state and the external input, so 3 variables, 8 possible combinations, and in the right part you will write down the flip-flop inputs and the output. But in this circuit you do not have any output, so you will only write the flip-flop inputs. So you have the equations. All right, you have the equations, you have the values, right? So just use these values and put those values into those equations and find out all of those columns. So JA, KA, JB, KB. So you'll get all those values based upon these equations and these values, just like a truth table. Okay, so once you get those values, then you will expand this state table and you'll write the next state in this state table, which are A plus and B plus. Okay, so which are A plus and B plus. Alright, so now to write down the values for A plus and B plus, we'll take the help of truth table of JK flip-flop, since this problem is related to JK flip-flop. Alright, so this is the truth table of JK flip-flop, and in the first row we can see when we want to calculate A plus, we don't need to consider all of them. We'll only need to consider everything related to A. So when we need to calculate A plus, we'll consider J, A, K, A and A from here, and when we calculate B plus, we'll consider J, B, K, B and B. Okay, so now we are calculating A plus. All right, so in case of the first row, J and KA, that means the flip-flop inputs are 0 and 0. So we go back to the truth table, we see the flip-flop inputs 0 and 0, and it produces the output of no change. Okay, so that means whatever is written here in the present state, it will not change. So for the first row, the present state is 0, so in the next state we write 0 again, so it did not change based upon the truth table. Now in the next row it's 0 0 again, so we write the same thing as the present state, so there's no change, present state 0, so next state would be 0. And in the third row we can see that the flip-flop inputs are 1 1, so if they're 1 1, then output is toggle. So that means whatever is given in the present state, it will be complemented. So the present state has 0, so after toggling, the next state value would be 1. Okay, so here we write 1. So similarly we can calculate all the values for A plus. Now when we want to calculate B plus, so now when we want to calculate B plus, we will only consider J, B and KB and B from this side. Okay, so let's say for the first row we have 1 0 as the flip-flop inputs, so we'll go back to the truth table, we see we find out 1 0 in the inputs and we see what the output is. So the output is 1. Since we are getting a value directly, we'll just put the value. Okay, so 1 0 produces 1, here we write 1 in the next state. So in the next part, in the next row, we see 0 1, so we go back to the truth table, we see that 0 1 produces 0 at the output, so again we are getting a value directly, so we'll just put that value as the next state. Okay, so we'll consider the we'll do the same stuff for all the rows and we'll complete this whole table. So once we complete the whole table, then just to get a more cleaner version, just to get a cleaner and neater version from this table, we'll just ignore this part. Okay, we'll just ignore this part and we'll write the whole table again. So this would be the new table after ignoring the flip-flop input parts. Okay, and from this part we can draw the state diagram just like before. So again we had two flip-flops, so if we have m number of flip-flops, okay, then we'll have 2 to the power m number of states. So we had 2 flip-flops, so we'll have 4 states, so 0 0 0 1 1 0 1 1. Okay, and we can see that from if the present state is 0 0, then for input x the next state would be 0 1. Here the present state is 0 0, for input 0, right, for input 0 the next state is 0 1. Okay, so similarly we can show the transitions for all the states just like the previous problem. Okay, so this is how you can build a state diagram from a circuit diagram. Okay, so that's it for this tutorial. In the next part we'll learn how we can actually do the reverse. Okay, that means we will build the circuit diagram from the state diagram. Okay, so see you in that tutorial.